Awesome, should be live now. Good morning, everybody. How's the audio this morning? I'll go ping the Discord. Audio's working good. Hey there, Connor. Cool. What else do I need to set up here? Oh yeah. Start casting. There, now you can see my keystrokes. Move some of this stuff out of the way. Cool, we'll give it like a minute or two. See if some more people trickle in here, and then I'll jump in. This is where we left off. Just go ahead and get this ready. We were doing stuff with, these like preprocessor macros. Okay, cool. Let's I'll get started here. People can continue to get on, but all right, so we had all these like conditioning on definition, like if def flag, that you can run this, otherwise don't. So now this is conditioning on text identity. If IDN is used to test if two text strings are equal. Spacing differences are not taken into account. Depending on the comparison result, the subsequent code will or will not be assembled. This allows us to create very flexible macros, which will depend, for example, on the argument name. To illustrate, let's create a pusher macro instruction, see listing 5.9. It will function exactly the same way as a push assembly instruction, but will also accept RIP and RFlags registers. Just making a macro pusher 1. That's interesting. See, what is push F? I don't even know what push F is. In x64 Nasim. What's push f? Let me push the current state of the flags register onto the stack. Oh, okay. You need a different command. So this just is like a push that supports like normal register pushing and stuff, but also flag pushing, right? Because it just checks here. If it's the R flag, then it'll just push R, or push F, sorry. And if it's anything else, it just does a normal push. That's interesting. I kind of want to try that. Well, I guess it doesn't really do anything. We'll just go on. Listing 510 shows that the two macros in listing 5.9 become after instantiation. It just becomes this. That's interesting. After the preprocessor, right? Yeah. As you can see, the macro adjusted its behavior based on the argument's text representation. Notice that else clauses are allowed just like for regular if. To make the comparison case insensitive, use if ident I directive. I for insensitive, I'm assuming. Conditioning on argument type. The Nasim preprocessor is a bit aware of the assembly language element's token types. It can distinguish quoted strings from numbers and identifiers. If there's a triple of if counterparts for this purpose. If ID to check whether its argument is an identifier. If stir for a string check, and if num to check whether it's in a number or not. Listing 511 shows an example of a macro which prints either a number or a string using an identifier. It uses several routines developed during the first assignment to calculate string length, output string, and output integer. Cool, that's interesting. So if it's an identifier, then we're going to print it. Well, like print a string. If it's a number, then it'll print the number using uint. Otherwise it's a string literal, right? And it'll say this isn't allowed. But what is this error macro? Maybe this isn't a macro. What is this? What's error? Okay. That's really cool. I didn't know that existed. That sounds useful. Cool. So yeah, this makes sense. I do kind of want to try this one. We'll call this macro argtypes.asm. I'll say macro print takes one argument, and then we need an end macro. Right up in here, we're gonna say like if if ID. So if one is an identifier, then we'll move RDI 1. What do you guys usually do? 4 or 2 spaces for chabs? Call print string. Oh, we don't really have print string. That's okay. We'll just write it out just for the sake of writing it out. Else, if num, right, if it's a number, then we need to like move RDI 1 again, and then call print uint. Else, error. This is the guy I like. String literals are not supported yet. Then we end if, and then we end if, and then we end macro, and then like down here you'd say like my hello is like some string with a new line and a null terminated. Okay, and then you go start. Why is that not showing? Okay, start print my print my hello, print 42, move RIX 60 syscall. Awesome, that's fun. The indentation is completely optional and is done for the sake of readability. Okay. In the case that the argument is neither string nor identifier, we use %error directive to force Nasim into throwing an error. Oh, it explains it here. If we had used fatal instead, we would have stopped assembling completely, and any further errors would be ignored. A simple error, however, will give Nasim a chance to signal about following errors too before it stops processing input files. That's interesting. Let's observe the macro instantiations in listing 512. Yeah, okay. How long is this section? All right, it's pretty long. So I'm gonna hold. Where was I here? Okay, stop here for a second. There's a few things I want to try that I just remembered after writing this assembly code that were suggested to me in the Discord. So one was actually a YouTube comment. Oh dear. Desync, why is bro writing an OS from scratch? To learn, and because I think it'll be fun. Alright, so here's what I want to try. I want to try where, how do I do this? Okay, wait, so 1 second here, I'm trying to find a, okay. This guy here. So this was that, remember that day when I was trying to run x64 ASM on Apple Silicon and I just kept running into all sorts of issues. This guy posted something, said I could try this, so I want to give that a shot. And then I also wanted to give I know I'd have to change the syscall numbers now, so this might just I might end up not designing to do this, but I thought it might be fun now that I know a little bit more assembly and I would be more familiar changing the things that need to be changed to make it compatible with Mac OS. I thought it might be worth a shot. So, and then there's also a language server that I kind of would like to set up. So I'm gonna make like a new window here. Actually, stick this over here. Stick this over here. Close that. I really just need that comment. Whoa. Yeah, okay. This is all I need right here. Cool, let's give that a shot. So, for example, if I want to make let me just make some example stuff. So let me make, I got this learning. Alright, let me make like a, oh, I already have a low level. Check it out, low level. What is this? I have some test stuff in here. Oh, perfect. Okay, let me get rid of like all this with this guy. I'm going to try. Oh, okay, so let me add like a proper exit. The syscode should be wrong. Oh, wait, that's not how you do it. Wrong syscall code. Same is true up here, but we're just gonna hold off for now. Okay, and then move RDI, or sorry, XOR RDI 0, and then, oh dear. syscall. So this will make us exit. Okay, so then down here, I'm gonna try what this guy suggested. So Nasim, do I have Nasim? I don't have Wishin. Nasim. Yeah, okay, I have Nasim. Nasim. Wait, I should have this thing. Okay, hello. Nasim -f Mako 64 -o hello dot o. That's probably what he meant. Hello dot asm. So now we have that dot o. So that assembled. And now if I arch x86 64 gcc hello.o dash o hello, it's yeah, it's freezing up on me. Alright, so that's a little bit discouraging, but so that didn't work. Oh well, it's not the end of the world. So the other thing, well, the other thing's not really worth setting up, but I can't do it locally, you know, so I'll go back to my code space, I guess. Get rid of that, get rid of this. Alright, we'll just keep going. But I'm glad I tried that at least. All programming languages have a notion of evaluation strategy. It describes the order of evaluation. It describes the order of evaluation in complex expressions. How would we evaluate this? Should we evaluate g of 1 and h of 4 first, and then let f act on the results, or should we inline g of 1 and h of 4 inside the body of f and defer their own evaluations until they're actually needed? Macros are evaluated by Nasim macro processor, and they do have a complex structure, as any macro instantiation can include other macros to be instantiated. A fine-tuning of evaluation order is possible because Nasim provides slightly different versions of macro definition directives, namely %define for a deferred substitution. If macro body contains other macros, they will be expanded after the substitution. Xdefine performs substitutions when being defined, then the resulting string will be used in substitutions. Assign is like to xdefine, but it also forces the evaluation of arithmetic expressions and throws an error if the computational result is not a number. To better understand the subtle difference between define and xdefine, take a look at the example shown in listing 513. We define I1. We define d I times 3, and then we xdefine xd I times 3. We assign I times 3. Okay. Wait. This becomes... Okay, key differences are that define may change its value between instantiations if parts of it are redefined. Okay. Xdefine has other macros on which it directly depends glued to it after being defined. Assign forces evaluation and substitutes values. Where xdefine should have left you with a preprocessor symbol equal to 4 plus 2 plus 3, assign will compute it and assign the value 9 to it. That's interesting. We will use the wonderful properties of assign to show some magic after becoming familiar with macro repetitions. Repetition. The times directive is executed after all macro definitions are fully expanded and thus cannot be used to repeat pieces of macros. But there is another way Nasim can make macro loops, by placing the loop body between rep and end rep directives. Loops can be executed only a fixed amount of times, specified as a rep argument. An example in listing 515 shows how a preprocessor calculates a sum of integers from 1 to 10 and then uses this value to initialize a global variable result. Assign 1 to X, you assign 0 to A, and then you repeat 10 times. Whoa. That's really interesting. I feel like my compiler is going to be able to use this kind of stuff a lot. Seems handy. After pre-processing the result, values correctly initialized to 55. You can check it manually. We can use exit rep to immediately leave the cycle. That's like a break, I guess. This is analogous to break instruction in high-level languages. Example: computing prime numbers. The macro shown in listing 57 is used to produce a sieve of prime numbers. It means that it defines a static array of bytes where each ith byte is equal to 1 if and only if I is a prime number. A prime number is a natural number greater than 1 such that it has no positive divisors other than 1 in itself. The argument is simple. 0 and 1 are not primes. 2 is a prime number. For each current up to limit, we check whether no I from 2 up to n divided by 2 is n's divisor. This is interesting. Assign limit is 15. Is prime is this, okay? It's a 0, 0, and a 1. Then you assign 3 to n. Well, that's probably why this is 3. Rep limit, assign current 1. Assign I 1, rep n over 2. You can just do this. I didn't know you could do this. Assign I to I plus 1, so you increment I. And then you db current. So you end up with something like this about whether or not it's prime. That's really interesting. That's crazy. Modify the macro the way it would produce a bit table, taking 8 times less space in memory. I'm not going to do that. For the macro, you'll probably have to copy and paste a lot. Alright, labels inside macros. There is not much we can do in assembly without labels. Using fixed label names inside macros is not quite common. When the macro is instantiated many times inside the same file, the multiply defined labels can produce clashes with stop compilation. Yes, that was a good answer. For ultimate pain and ultimate gain. There's an option to use macro local variables, which is a label you cannot access outside of current macro instantiation. In order to do that, you can prefix such label name with a double % as follows: %% label name. Each macro local label will get a random prefix which will change between macro instances but will remain the same inside one instance. Listing 519 shows an example. Listing 520 contains the pre-processing results. Okay. The macro my macro is instantiated 3 times. Each time the logical label gets a unique name. The base name, after a double %, becomes prepended with a numerical prefix different in each instance. The first prefix is at 0, the second is at 1, and so on. That's interesting. Conclusion: you can think about macros as a programming meta language executed during compilation. It can do quite complex computations and is limited in 2 ways. These computations cannot depend on user input, so they can only operate on constants. The cycles can be executed no more than a fixed amount of times. It means that while instructions are impossible to encode. Yeah, okay. Translation. A compiler usually translates source code from one language into another language. Yeah. In case of translation from higher level languages into machine code, this process incorporates multiple inner steps. During these stages, we gradually push the code IR, an intermediate representation, towards the target language. Each push of IR is closer to the target language. Right before producing assembly code, the IR will be very close to assembly, so we can flush the assembly into a readable listing instead of encoding instructions. Not only is translation a complex process, it also loses information about source code structure. So reconstructing readable high-level code from the assembly file is impossible. A compiler works with atomic code entities called modules. A module usually corresponds to a code source file, but not a header or include file. Each module is compiled independently from the other modules. The object file is produced from each module. It contains binary encoded instructions, but usually cannot be executed right away. There are several reasons. For instance, the object file is completed separately from other files, but refers to outside code and data. It is not yet clear whether the code or data will reside in memory or the position of the object file itself. The assembly language translation is quite straightforward because the correspondence between assembly mnemonics and machine instruction is almost one-to-one. Apart from label resolution, there is not much non-trivial work. Thus, for now, we will concentrate on the following compilation stage, namely linking. Cool. This is all helpful because this is like all stuff we're gonna have to deal with Lovely, right? With our compiler. Linking. Let's return to our first examples of assembly programs. To transform a hello world program from source code to executable file, we use the following two commands. Yep. We use Nasim first to produce an object file. Yep. Then we use another yep to link it. All right. Elf. We know about elf. Allows for three types of files: relocatable object files, or .o files, produced by the compiler or assembler. Relocation is a process of assigning definitive addresses to various program parts and changing the program code the way all links are attributed correctly. We're speaking about all kinds of memory accesses by absolute addresses. Relocation is needed, for example, when the program consists of multiple modules which are referencing one another. The order in which they will be placed in memory is not yet fixed, so the absolute addresses are not determined. Linkers can combine these files to produce the next types of object files. Executable object file can be loaded in memory and executed right away. It is essentially a structured storage for code, data, and utility information. Shared object files can be loaded when needed by the main program. They are linked to it dynamically. In Windows OS, there are well-known DLL files. In Starnix systems, their names often end in .so. The purpose of any linker is to make an executable or shared object file given a set of relocatable ones. In order to do it, a linker must perform the following task: relocation and symbol resolution. Each time a symbol, function, or variable is dereferenced, a linker has to modify the object file and fill the instruction part corresponding to the operand address with the correct value. An ELF file starts with the main header, which stores global meta information. See listing 521 for a typical ELF header. The hello file is a result of compiling a hello world program shown in listing 2.4. Okay. So a lot of like meta information, no? ELF files then provide information about a program that can be observed from 2 points of view. Linking view, consisting of sections, is described by a section table, which is accessible through readelf-s. Each section in turn can be raw data to be loaded into memory, formatted metadata about other sections used by a loader, linker, or debugger. Code and data are stored inside sections. Execution view consists of segments. It is described by a program header table, which can be studied using readelf-l. Take a closer look at it. Okay, each entry can be described, some kind of information the system needs to execute the program. An ELF segment containing 0 or more instructions. They have the same set of permissions enforced by virtual memory. Each segment has a starting address and is located in a separate memory region consisting of consecutive pages. After revising listing 521, we notice it describes precisely the position and dimensions of program headers and section headers. We start with the sections view since the linker works mainly with them. Okay, I'm going to turn on this thing. There we go. Assembly language allows manual section controls. Nasim's section corresponds to object file sections. You have already seen a couple of those, namely .text and .data, yeah? The list of the most used sections follows. The full list can be found in 24. .text stores machine instructions. The row data stores read-only data. That's what a row stands for, or read-only. Data is the global variables. BSS stores readable and writable global variables initialized to 0. There is no need to dump their contents into an object file, as they are always filled with zeros anyway. Instead, a total section size is stored. An operating system may know faster ways of initializing such memory than zeroing it manually. In assembly, you can put data there here by replacing resb, resdub, and similar directives. Sorry, by placing, not replacing, these and similar directives after the section.bss. Rel text stores relocatable table. For the text section, it is used to memorize places where a linker should modify .text after choosing the loading address for a specific object file. Rel data stores a relocatable table for data. This is a handy chart. Debug stores symbol data used to debug it. Line defines correspondence with pieces of code and line numbers in source code. Stir tab stores character strings. It is like an array of strings. Okay. Symtab stores a symbol table. Whenever a processor defines a table, and Nasim will create a symbol for it. Relocatable object files. Let's investigate an object file obtained by compiling a simple program shown in listing 522. This is our file. This program uses external and global directives to mark symbols in a different way. These two directives control the creation of a symbol table. See, we've already used these. This. Oh, wait, where's extern? I'm not saying extern. Extern. Oh, this guy somewhere. Do not confuse global and local symbols with global and local labels. Oh dear. Okay, the GNU bin utils is a collection of binary tools used to work with object files. It includes several tools used to explore object file contents. Several of them are of particular interest to us. If you only need to look up a symbol name, use nm. Use objdump as a universal tool to display general information about an object file. In addition to ELF, it does support other object file formats. If you know that the file is in ELF format, readelf is often the best and most informative choice. Let's feed this program to objdump to produce the results shown in listing 523. You get all this stuff, okay? We are shown a symbol table where each symbol is annotated with useful information. What do its columns mean? 1. 1, I'm guessing, is the first column, this guy. The virtual address of the given symbol. For now, we do not know the section starting addresses, so all virtual addresses are given relative to section start. For example, data var 1 is the first variable stored in .data. Its address is 0, and its size is 8 bytes. That's interesting. The second variable, data var 2, is located in the same section with a greater offset of 8 next to data var 1. As somewhere is defined as extern, it is obviously located in some other module. So for now, its address has no meaning and is left 0. A string of 7 letters and spaces, each characterizes a symbol in one way. Some of them are of interest to us. LG, local, global, or neither. That's what this is over here. B, I guess, is not of interest to us. C, neither. C, D. E, I is a link to another symbol or an ordinary symbol. Redstone tutorials. Hi, what are we doing today? Wait, chat. Does he read chat? I do read chat. I'm learning assembly because I want to make an operating system. That's what we're doing today. So I'm kind of reading this book. It's Low-Level Programming by Igor Zhirkov. What section does this label correspond to? Und for unknown sections. Symbol is referenced but not defined here. ABS means no section at all. Usually this number shows an alignment or its absence. Symbol name. Okay. So those are the columns. For example, let's investigate the first symbol shown in listing 523. It is F, a file name, D, only necessary for debug purposes, and L, local to this module. For example, let's investigate the first symbol shown in listing 523. It is F, a file name, D, only necessary for debug purposes, L, local to this module. The global label _ start, which is also an entry point, is marked with the letter G in the second column. As the addresses in the symbol table are not yet the real virtual addresses, but ones relative to sections, we might ask ourselves, how do these look in machine code? Nasim has already performed its duty, and the machine instructions should be assembled. crust op, are those addresses given manually or automatically allocated by memory? I do not know. Nasim has already performed its duty, and the machine instructions should be assembled. We can look inside interesting sections of object files by invoking objjunct with parameters -d for disassemble and optionally -m intel mnemonic to make it show intel-like syntax rather than AT&T one. Listing 5.2 shows the results. How to read disassembly dumps. The left column usually is the absolute address where the data will be loaded. Before linking, it is an address relative to the section start. The second column shows raw bytes as hexadecimal numbers. The third column can contain the result of disassembling the assembly command mnemonics. Redstone tutorials. Automatically, the linker determines which address to give it based on a starting point. Gotcha. Yeah, that makes sense. Okay. Or entry point, yeah. Crust also based on the data type, right? As it did with extern. Yep, it's more based on which section it's in. Hey, Bacon. What's up? Cool. So this is like a dump. The move operand in section.text with offsets 0 and 14 relative to section start should be data var1 address, but it's equal to 0. The same thing happened with BSS var. It means the linker has to change compiled machine code, filling the right absolute address and instruction arguments. To achieve that, for each symbol, all references to it are remembered in relocation table. As soon as the linker understands what its true virtual address will be, it goes through the list of symbol occurrences and fills in the holes. A separate relocation table exists for each section in need of one. To see the relocation tables, use readelf -- relogs. See listing 525. Okay. There's a lot of different things you can do. An alternative way to display the symbol table is to use a more lightweight and minimalistic NM utility. For each symbol, it shows the symbol's virtual address, type, and name. Note that the type flag is in different format compared to objdump. See listing 526 for a minimal example. Cool. Executable object files. The second type of object file can be executed right away. It retains its structure, but the addresses are now bound to exact values. We will take a look, okay? Going to compile it as usual using our friend Nasim -f-elf64 and then link it with LD with the previous object file obtained by compiling the file, okay? When we do it, we get this. That's our symbol table. The flags are different. Now the file can be executed, execp, and there are no more relocation tables. The has reloc flag is cleared. Virtual addresses are now intact, and so are addresses in code. This file has to be reloaded and executed. It retains a symbol table, and if you want to cut it out, making the executable smaller, use the strip utility. Also, if I may ask, why you're learning the linker pipeline? Good question. I'm just going through this book, and this was the next section. So I don't know if I have a really good reason to be learning it. But I'm going sort of fast because I'm pretty sure I don't need to fully understand all of this. So that's why I'm going sort of fast. But yeah, it was just the next section in the book I'm going through. Why does LD issue a warning if start is not marked global? Look at the entry point address in this case by using readelf. Okay. Find out the LD option to automatically strip the symbol table after linking. Alright, we're going to skip those. Dynamic libraries. Almost every program uses code from libraries. There are two types of libraries, static and dynamic. Static libraries consist of several relocatable object files. These are linked to the main program and are merged with the result executable file. In the Windows world, these files have an extension .lib. In the Unix world, these are either .o or .a archives holding several .o files inside. Dynamic libraries are also known as shared object files. The third of 3 object file types we have defined previously. Yep. They're linked with the program during its execution. In the Windows world, these are infamous DLL files. In the Unix world, these files have an SO extension, shared objects. While static libraries are just undercooked executables without entry points, dynamic libraries have some differences. Redstone, I'm curious, do you suggest that I don't learn about this right now and just like jump on to the next section? Because the next section would be, well, I'm almost done really, so I might as well finish at this point. The next is interrupts and system calls. And then I think there's one more after that, models of computation. And then it goes on to C. Models of computation is all about fourth, which I have no idea what it is, but it sounds interesting. And then you go on to C. So, hello, gaming op. I think since I'm so close, I might as well finish it at this point, right? Yeah, okay. Well, I think you're not really loading binaries anytime soon. No hate, so not really. I do strongly recommend reading section 6. Section 6 was interrupts and system calls. Sure. Yeah, fair, very fair. So, yeah, no, that's a good point. I'm really close though, so I'm just gonna like kind of skim through the rest of it, and then, or I mean, I could just skip it too, whatever. It's mostly just code examples and an assignment that I'm not gonna do anyway. So, and then a summary. So it's really just like one more page of code examples. Oh, where was I? I was like here, I think. All right, I'll read through some of this. While static libraries are just undercooked executables without entry points, dynamic libraries have some differences, which we are going to look at now. Dynamic libraries are loaded when they're needed. They're object files on their own. They have all kinds of meta information about which code they provide for external usage. This information is used by a loader to determine the exact address of exported functions and data. What part of the OS are we focusing on today? The OS doesn't really exist yet. I'm just kind of trying to learn, I'm following this book to learn assembly in C and hoping to use that to, well, definitely using assembly to make the language. I'm actually not going to use C, but I might learn it anyway. We'll see. I'm not entirely certain about C yet, but definitely want to like keep learning assembly so I can know that because I'm going to be using that a bunch. Dynamic libraries can be shipped separately and updated independently. It is both good and bad. While the library manufacturer can provide bug fixes, he can also break backward compatibility by, for example, changing function arguments, effectively shipping a delayed action mine. I'm curious, what do you guys think about learning C? So for those who are not like following everything or aren't updated on everything, I have like this series going, which is building an operating system from scratch, which has pretty much just been learning assembly so far, which is fun. And then I have another series going that's called building a programming language from scratch or something like that, where I'm making a language called Lovely to write the operating system in. And so I'm not actually going to be using C or Rust, but should I learn C nonetheless, even though I'm not necessarily going to be writing it? I know that pretty much every learning resource out there uses C, so that's like a pretty big motivating factor. But on the other hand, I'm not really going to be writing much C. It would also be fun just to learn C. Bacon says, LOL, you should learn C. Python is written in C. Everything's written. Yeah, I know everything's written in C. It'll make writing assembly a lot easier, will it? Gaming. So how are you going to get started with OS development? Once I finish learning about assembly here, I think I'm going to try to write a bootloader, and then we're going to go from there. But I've got a programming language to get into working shape before we can get much past that point. So this is definitely a long-term project. So for anybody that's hoping for a quick operating system, you might be disappointed. Sorry. All right, Bacon is saying I should learn C. Let me do a quick poll. What do you guys think? Vim is written in C. That is a good point. See, but Helix is written in Rust. C is the closest language to ASM. Learn C. All right. Well, let me just do a formal poll. I'm pretty convinced, but let me just make sure. Should I learn C, even though it won't be used in the OS? Yeah, Linux is C, Windows is C. May I interrupt to say learn Rust? I do or already know Rust. I'm writing my language in Rust. So Rust was my initial idea to write the operating system in. Yeah, no, you may not interrupt. Yeah, no, I use Rust a bunch. All right, we have 5 votes, 6 votes, and they're all for yes to learn C. So I guess we'll be learning C, no? 7 votes, all for C. All right, well, we'll be learning C. Should be fun. I'm actually kind of excited for it. Okay, a program can work with any amount of shared libraries. Such libraries should be loadable at any address, otherwise they would be stuck at the same address. Rust is more of a C++ alternative. Exactly, yeah. What do you mean it's not used in writing OS? You want C. Wait, what do you mean by that, Nihan Wasura? What do you mean it's not used in writing OS? You want C? There's no C alternative. Don't people call Zig Bacon the C alternative? But yeah, I understand that it's not exactly the same. Once you read the next section, it will show you how understanding C will help you understand Unix, because those syscalls have wrapper functions that are written in C. Yeah, I do know that. You just want to mention Rust. Yeah, Rust is good. I really like Rust, actually, generally. There's definitely some things I really don't like about it, but there's some things I really do like about it. Okay, otherwise they'd be stuck in the same address, which pushes exactly the same situation as when we were trying to execute multiple programs in the same physical memory address space. There are 2 ways to achieve that. Okay, maybe Zig. It's just too new to be reliable. Yeah, I played with Zig for a little while, and yeah, it just felt like it was too new. Like, there's some really good ideas going on, especially like comp time, but the language server was pretty bad. The package manager was like not existent, and it's just, yeah. V, I haven't seen V. Hello, Apple Pumpcaster. All right, where were we? Okay, effectively the data section would be relocated anyway because of its mutable nature. Yeah. Okay, another problem is the text. We can write position-independent code. It is now possible to write code which can be executed no matter where it resides in memory. For that, we have to get rid of absolute addresses completely. These days, processors support RIP relative addressing like move RIX, RIP plus 13. This feature facilitates PIC generation. This technique allows for .text section sharing. Today, programmers are strongly encouraged to use PIC instead of relocations. Whenever you are using non-constant global variables, you prevent your code from being re-enterable, that is, being executable inside multiple threads simultaneously without changes. That makes sense. It's like not thread safe. Consequently, you will have difficulties reusing it in a shared library. It is one of many arguments against global mutable state in a program. Yep. Zoe Cyber. Hi, just joining. What kind of OS are you making? Yes, Bacon's right. We're just learning ASM at the moment. So you're trying to use raw x86 assembly, raw x64, so 64-bit for writing everything, like even after you got the bootloader and all, so the ultimate pain. No. That's not right. I'm making a language called Lovely, like a programming language, and we're going to use that. We're not going to write everything in ASM. But my language needs to compile to ASM, so that's just like another reason I need to. Right, yeah, okay. Okay, where were we? Redstone says I just jump into it and learn the things as you go. Yeah, that's how I started. Yes, x64 in protected mode. We'll show you how to build a minimal shared object now. Okay, I'm going to skip this part. All right, go to loader. Loader is part of the operating system that prepares executable files for execution. Includes mapping its relevant sections into memory, initializing .bss, and sometimes mapping other files from disk. The program headers for file symbols.asm shown in listing 522 are shown in listing 532. What resources are you using to learn assembly, Kaya? I'm using this book right now. It's called Low Level Programming by Igor Zhirkov. Will AI replace me? Good question. Maybe this is AI. Maybe it has already. Loader. You're trying to build your own custom Linux for hardware hacking. Awesome. Yeah, we already read that. Okay, and then we get that. Okay. And then we're not going to do the assignment. So we're done. We're going to jump on to interrupts and system calls. Doesn't that just make you so excited? Okay, in this chapter, we are going to discuss two topics. First, as von Neumann architecture lacks interactivity, the interrupts were introduced to change that. Although we are not diving into the hardware part of interrupts, we are going to learn exactly how programmer views the interrupts. Yeah, we're all just bots here. Yep, Bacon nailed it. We're going to learn exactly how a programmer views the interrupts. Additionally, we will speak about input and output ports used to communicate with external services. Second, the operating system OS usually provides an interface to interact with resources. It controls memory files, CPU, etc. This is implemented via system calls mechanism. Transferring control to the operating system routines requires a well-defined mechanism of privilege escalation, as we're going to see how it works in the Intel 64 architecture. When we were extending the von Neumann architecture to work with external devices, we mentioned interrupts only as a way to communicate with them. In fact, there's a second feature, input-output I/O ports, which complements it. It complements it and allows data exchange between CPU and devices. Cool. The application can access I/O ports in two ways: through a separate I/O address space. Are you going to make a GUI or just stay text-based like DOS, Kaya? I would love to make a GUI. Making a GUI sounds like a ton of fun. But I know that if I do, that'll be quite a ways down the road. So I wouldn't be hoping for that anytime soon. But I would love to. I think the long-term plan is to, make a GUI. When you're working on the OS, have the Intel Programmer's Manual of Volume 3 open. It really helped me. Okay. Will do. I have it downloaded. Or I did. I'm not sure what happened to it, actually. Okay, there are 2 to the 16th 1-byte addressable I/O ports. That's a lot. From 0 through FFFFH. H. What is this? This isn't hex. There's no H in hex. The commands in and out are used to exchange data between ports and EAX registers or its parts. Write my OS in Ada. Oh no, I can't do that. It's a hexadecimal suffix. Oh, so it's just FFFF. The H just means hex. Is that what you're saying? The permissions to perform writes and reads from ports are controlled by checking IOPL, IO privilege level fields of rflags registers. Yeah, okay, cool. Thank you. IO permission bitmap of task state management. Oh, sorry, not management. Sorry. My brain is kind of fried. Of a task state segment. We will speak about it in section 6.1.1 through memory mapped IO. A part of address space is specifically mapped to provide interaction and such external devices that respond like memory components. Consecutively, any memory addressing instructions, move SB, etc., can be used to perform I/O with these devices. Standard segmentation and paging protection mechanisms are applied to such I/O tasks. The IOPL fields in rflags register work as follows. If the current privilege level is less or equal to the IOPL, the following instructions are allowed to be executed. In and out, normal input output, ins and outs, string input and output. Oh, okay, so it's in string, out string. CLI and STI, clear, set, interrupt flag. Thus, setting IOPL in an application individually allows us to forbid it from writing even if it is working at a higher privilege level than the user applications. Additionally, Intel 64 allows an even finer permission control through an IO permission bitmap. If the IOPL check has passed the processor checks and the bit corresponding to the use port, the operation proceeds only if this bit is not set. The IO permission bitmap is part of task state I keep saying management, I don't know why. Part of task state segment, which was created to be an entity unique to a process. However, as the hardware task switching mechanism is considered obsolete, only one TSS and IO permission bitmap can exist in long mode. Hey, Uncool, what's up? Do I have a Discord? Yeah, totally. Let me get you the link. How do I do this? Here we go. Oh no, that's not gonna work. There we go. There's the Discord link for you gaming. Saurav Kumar got late. It's alright. Yeah. The link's not in the description for this video, I don't think yet. I should probably do that, but building an OS, bold task, not gonna lie, but wish you the best. Thank you, appreciate it. Yeah. We'll see how far it gets. Alright, TR register and task state segment. There are some artifacts from the protected mode that are still somehow used in long mode. A segmentation is an example, now mostly used to implement protection rings. Another is a pair of a TR register and task state segment control structure. Thus, TR register holds the segment selector into the TSS descriptor. The latter resides in the GDT global descriptor table and has a format similar to a segment descriptors. Likewise, for segment registers, there is a shadow register, which is updated from GDT when TR is updated via LTR, load task register instruction. The TSS is a memory region used to hold information about a task in the presence of a hardware task switching mechanism. Since no popular OS has used it in protected mode, this mechanism was removed from long mode. However, TSS in long mode is still used, albeit with a completely different structure and purpose. These days, there is only one TSS used by an operating system, with the structure described in Figure 6.1. Okay. Interesting. Task state management in long mode. The first 16 bits store an offset to an input-output port permission map, which we already discussed in section 6.1. The TSS then holds 8 pointers to special interrupt stack tables, ISTs, and stack pointers for different rings. Each time a privilege level changes, the stack is automatically changed accordingly. Usually the new RSP value will be taken from TSS field corresponding to the new protection ring. The meaning of ISTs is explained in section 6.2, and sure enough, here's 6.2. Interrupts. Interrupts allow us to change the program control flow at an arbitrary moment in time. While the program is executing external events, the device requires CPU attention, or internal events, division by 0 and sufficient privilege level to execute an instruction at non-canonical address, may provoke an interrupt, which results in some other code being executed. This code is called an interrupt handler and is part of an operating system or driver hardware. Cool. Sorry, driver software. In 15, okay, Intel separates external asynchronous interrupts from internal synchronous exceptions, but both are handled alike. Each interrupt is labeled with a fixed number which serves as its identifier. For us, it is not important exactly how the processor acquires the interrupt number from the interrupt controller. When the nth interrupt occurs, the CPU checks the interrupt descriptor table, which resides in memory. Analogously to GDT, its address and size are stored in IDTR. Figure 6.2 describes the IDTR. Okay. Each entry in IDT takes 16 bytes, and the nth entry corresponds to the nth interrupt. The entry incorporates some utility function as well as address of the interrupt handler. Figure 6.3 describes the DPL descriptor privilege level. Current privilege level should be less or equal to DPL in order to call this handler using int instruction. Otherwise, the check does not occur. Type 1110 interrupt gate if is automatically cleared in the handler, or was your 1111 trap gate IF is not cleared. The first, I don't understand this. The first 30 interrupts are reserved. It means that you can provide interrupt handlers for them, but the CPU will use them for its internal events such as invalid instruction encoding. Other attempts can be used by the system programmer. When the IF flag is set, the interrupts are handled, otherwise they're ignored. What are non-maskable interrupts? What is their connection with the interrupt with code and IF flag? The application code is executed with low privileges in ring 3. Direct device control is only possible on higher privilege levels. When a device requires attention by sending an interrupt to the CPU, the handler should be executed in a higher privilege ring, thus requiring altering the segment selector. What about the stack? The stack should also be switched. Here we have several options based on how we set up the IST field of interrupt descriptor. If the IST is 0, the standard mechanism is used. When an interrupt occurs, SS is loaded with 0, and the new RSP is loaded from TSS. The RPL field of SS is then set to an appropriate privilege level. The old SS and RSP are saved in the new stack. Okay. If an IST is set, one of the 7 ISTs is defined in TSS is used. The reason ISTs are created is that some serious faults, non-maskable interrupts, double faults, etc., might profit from being executed on a known good stack. So system programmer might create several stacks even for ring 0 and use some of them to handle specific interrupts. There is a special int instruction which accepts the interrupt number. It invokes an interrupt handler manually with respect to its descriptor contents. It ignores the IF flag. Whether it is set or cleared, the handler will be invoked. To control execution of privileged code using int instruction, a DPL field exists. Before an interrupt handler starts its execution, some registers are automatically saved into stack. These are SS, RSP, RFlag, CS, and RIP. See a stack diagram in figure 6.4. Note how segment selectors are padded to 64-bit with zeros. Okay. Sometimes an interrupt handler needs additional information about the event. An interrupt error code is then pushed onto stack. Okay. This code contains various information specific for this type of interrupt. Many interrupts are described using special mnemonics in Intel documentation. For example, the 13th interrupt is referred to as GP, General Protection. You will find a short description of some interesting interrupts in table 6.1. There's, for example, divide error, non-maskable external interrupt, breakpoint, invalid instruction opcode, a fault while handling interrupt, general protection, page fault. Not all binary code corresponds to correctly encoded machine instructions. When RIP is not addressing a valid instruction, the CPU generates the UD interrupt. The GP interrupt is very common. It is generated when you try to dereference a forbidden address which does not correspond to any allocated page, when trying to perform an action requiring a higher privilege level, and so on. The PF interrupt is generated when addressing a page which has its present flag cleared in the corresponding page table entry. This interrupt is used to implement the swapping mechanism and file mapping in general. The interrupt handler can load missing pages from disk. The debuggers rely heavily on the BP interrupt. When the TF is set in R flags, the interrupt with the code is generated after each instruction is executed, allowing a step-by-step program execution. Evidently, this interrupt is handled by an OS. It is thus an OS's responsibility to provide an interface for user application that allows programmers to write their own debuggers. Okay, sum up. When an nth interrupt occurs, the following actions are performed from a programmer's point of view. The IDT address is taken from IDTR. The interrupt descriptor is located starting from 128 times nth byte of IDT. The segment selector and the handler address are loaded from the IDT entry into CS and RIP, possibly changing privilege level. The old RS, RSB, R flag, CS, and RIP are stored in the stack as shown in figure 6.4. For some interrupts, an error code is pushed on top of a handler stack. It provides additional information about interrupt cause. If the descriptor's type field defines it as an interrupt gate, the interrupt flag IF is cleared. The trout gate, however, does not clear it automatically, allowing nested interrupt handling. If the interrupt flag is not cleared, I should end this poll, shouldn't I? There we go. If the interrupt flag is not cleared immediately after the interrupt handler start, we cannot have any kind of guarantees that we will execute even its first instruction without another interrupt appearing asynchronously and requiring our attention. Alright, the interrupt handler is ended by a IRETQ instruction, which restores all registers saved on the stack, as shown in figure 6.4, compared to the simple call instruction, which restores only RIP. Alright, and then we have our friend syscalls. Are, as all you already know, functions that the OS provides for user applications. This section describes the mechanism that allows their secure execution with higher privilege level. The mechanisms used to implement system calls vary in different architectures. Overall, any instruction resulting in an interrupt will do. For example, division by 0 or any incorrectly encoded instruction. The interrupt handler will be called and then the CPU will handle the rest. In protected mode on Intel architecture, the interrupts with code OX80 was used by StarNix operating systems. Each time a user executed int 0x80, the interrupt handler checked the register contents for system call numbers and arguments. System calls are quite frequent and you cannot perform any interaction with the outside world without them. Interrupts, however, can be slow, especially on Intel 64, since they require memory accesses to IDT. So in Intel 64, there's a new mechanism to perform system calls, which uses syscall and sysret instructions to implement them. What's sysret? I've never used that. Compared to interrupts, the mechanism has some key differences. The transition can only happen between ring 0 and ring 3. As pretty much no one uses ring 1 or ring 2, this limitation is not considered important. Interrupt handlers differ, but all system calls are handled by the same code with only one entry point. Some general purpose registers are now implicitly used during system call. RCX is used to store old RIP. I did not know this. R11 is used to store old R flags. I did not know either of these. That's good to know. Model specific registers. System return, basically Linux giving control back to the program. Okay. Thanks, Redstone. Redstone, you should get on the Discord if you're not on there. Seems like you know your stuff. Sometimes when a new CPU appears, it has additional registers, which other more ancient ones do not have. Quite often, these are so-called model-specific registers. When these registers are rarely modified, their manipulation is performed via two commands, rdmsr to read them and wrmsr to change them. These two commands operate on the register identifying number. rdmsr accepts the MSR number in ECX, returns the register value in EDX EAX. WRMSR accepts the MSR number in ECX and stores the value taken from it EDX EAX in it. Oh, you're already on there. Awesome. Doesn't get control automatically. Interesting. You learned something new today. Syscall. Oh, here we go. Sysret. The syscall instruction depends on several MSRs. Star MSR number that, which holds two pairs of CS and SS values for system call handler and for sysret instruction. Figure 6.5 shows its structure. I'm making a kernel and now I just have to write drivers and make a mounting thing because I wrote my own file system. Dude, that's so cool. I just heard Discord blowing up, so that might be what's happening. Oh no, just a bunch of people have joined. Okay. Oh yeah, I see you on here. There we go. You just joined. Awesome. Cool. And then there's L star, which holds the system call handler address, the new RIP. Then there's SF mask, the San Francisco mask, which shows which bit and R flags should be cleared in the system call handler. The syscall performs the following actions. It loads the CS from star. It changes R flags with regards to SF mask, saves the RIP and RCX, and initializes RIP with L star value and takes new CS and SS from that star. Okay. This is all stuff I can refer back to when I actually need it. I don't feel the need to memorize all of this right now. Note that we can explain why system calls and procedure accepts arguments in slightly different sets of registers. The procedures accept their fourth argument RCX, which as we know is used to store the old RIP value. Contrary to the interrupts, even if the privilege level changes, the stack pointer should be changed by the handler itself. System call handling ends with sysret instruction, which loads CS and SS from star and RIP from RCX. As we know, the segment selector change leads to a read from GDT to update its paired shadow register. However, when executing syscall, these shadow registers are loaded with fixed values and no reads from GDT are performed. Here are these two fixed values in deciphered form. Okay. And then there's these. However, the system programmer is responsible for fulfilling a requirement. GDT should have the descriptor corresponding to these fixed values. So GDT should store two particular descriptors for code and data specifically for syscall support. In this chapter, we have provided an overview of interrupts and system call mechanisms. We have studied their implementation down to, okay. Cool. Okay, so we're already done with that one. Okay, so this is the last chapter prior to potentially beginning C, although I'm not really totally convinced yet that not learning C. It sounds fun to learn C for sure, but it also sounds like a lot of time that I'm not really gonna be using it, you know? I mean, for reading it's nice, but I'm already fairly comfortable reading C. I used to kind of know C. So I don't know. What do you guys think? I don't know. Well, we got to get through this first anyway. Although, unless this would be a good stopping point. Because this is a pretty long one, right? What book is this? What book is this? This is Low Level Programming by Igor Zhirkov. I'll write it in chat here. Low Level Programming by Igor Zhirkov. You can write the OS in Rust too. That was the original plan, and then I decided to write it in my own language. Assembly is used to set the table so that the processor knows where to look for stuff. You could do that too using C. I learned C, says Bacon, one of the simplest languages to understand. But I feel like I already understand it. It's just that I don't know all the syntax. What about Zig? I played with Zig. I don't think I'm gonna learn it just for this though. Look, learning C would be a fun learning exercise and stuff, and I know I'd learn a lot. It's just I'm not actually going to be using it, so I'm wondering if it's worth my time. And like it would just delay getting to the actual operating system like more than we already are. And for that reason, I'm wondering if it's totally worth it. Yeah, okay, so this is a longer one, and then it's C, okay. Like the other option I think would be finish this section and then I don't know, and then start trying to write a bootloader, like just jump into the operating system and learn as we go. Or spend a while learning C first and then not use it. I wonder if the poll would give the same results if I worded it that way. Okay, where am I? Okay, I already did that a long time ago, sorry. Where's my place? Here we go. You'd say write the bootloader now because the first stage will be in ASM whether you like it or not. Yeah, I know. First stage is going to be ASM anyway, and the second stage is going to be my own language and not C. I don't think C is ever going to be a stage. So that's why I'm doubtful about learning C. Probably a good idea to use what I know. Yeah, I'm definitely not. I know I'm not using C. Let me do a new poll. Should I learn C? Yes, even though it will delay OS. No, because I'm not going to use it. What do you guys think now? Bacon, well, given that all the drivers are literally everything is written in C, it would be really easy to just customize previous work made by others to fit your OS. It would save so much time. Yeah, that makes sense. Redstone says I can do that with my own language too. I think I can read this next section in one day. I feel like I probably could. I'll probably try to finish that tomorrow. Because they're mostly written for Linux, and that is its own structs and including. Hold on. Zig is a better C, and it will make learning C easier later. Integrates really easily with C, C++. Yeah, I'm pretty sure I'm not going to do Zig. If I don't do my own language, I'll do Rust, but I'm not going to do Zig. You think my own language would be even slower? Totally. Like way slower. Because I have to write it first. But we're working on it. Yeah, it's learning. It's a learning thing. Yeah, the poll is about the delays introduced by learning C, which is a good point. I could just be learning C while I'm writing my own language. Because I basically have a lot of work on my own language to do on those other streams before I can start writing like higher level operating system stuff, and so I could just be learning C while I do that, because I'll need something to do. Or I could just spend all my time working on the language. Alright, well, I'll think about it. Maybe I will learn C. Because I'm almost done with this section. I do kind of want to keep going with this book. C would help me with writing your own language as well. Yeah. Especially if I decide to do manual memory management for my language, right? All right. Well, yeah. Go the Terry Davis route. That's like what I'm doing. Except it's not Holy C, it's lovely. Gaming's back. It's just the de facto language for what you want to do. It is. Yeah. All right, cool. Well, we'll stop here, I think. Database and operating system. What do you think the most interesting to build from scratch to learn, gain knowledge? I'm about to start trying to do the operating system. I've never done a database. I've often thought that making a database, though, would be super fun. And I feel like really hard to get right. All right, well, I'll stop the stream there. Hoping to, maybe later today I'll do a lovely stream. Keep working on that, and then tomorrow probably morning I'll do another one of these, trying to maybe finish this chapter or this section on assembly, and then maybe start C. We'll see about the C. But thanks everybody for getting on and for all the help. Appreciate it a lot. How do I stop streaming? Oh yeah, there we go. Nice meeting you too, Apple. Bye, Redstone.